Okay, I deeply express gratitude to organizers and thank you for invitation. So my talk concerned with the volume growth in the component of the fibered Dehn twist. So this is joint work with my colleagues, Myung-gi Kwon and Junyoung Lee. So let's see. Okay, so today's talk has 4 contents. The first section I will explain what the slow volume growth. This is some kind of entropy type quantity for diffeomorphism. And I will explain what the Liouville domain is. Liouville domain is certain symplectic manifold with boundary, and boundary has nice structure, which is called a contact manifold. And for certain Liouville domain, we can define the fibered Dehn twist, which is a symplectomorphism on the Liouville domain. And we want to investigate the slow volume growth of the fibered Dehn twist. So we will use so-called wrapped flow homology, which is some Lagrangian flow homology for a non-compact manifold, or one can regard this as the open string analog of symplectic homology. And I will finally mention what our main result is. Okay, so let's define the slow volume growth. We just consider some Riemannian manifold. I mean, that's M is smooth manifold with dimension n, and G is some metric. And we want to consider some diffeomorphism, which is compactly supported, because we don't assume that M is compact. So here the compact support of diffeomorphism means that it consists of points which is not identity, and we just take closure. And we assume that support of diffeomorphism is compact. Now the definition of slow volume growth of phi is defined as following. So here we just consider, okay, so here sigma is some embedded smooth I cube inside the manifold M, and we consider each image under the M iteration of given diffeomorphism, and we want to consider each volume. So we want to know some grossness of the volume of cube under the iteration of this map. So this is what does it mean. So it measures the grossness, polynomial grossness of volume iteration of cube, and we consider all cube inside the manifold and take the sup. So roughly speaking, this strange notion means that we want to know how given diffeomorphism is complicated. So intuitively, this quantity measures the complexity of given diffeomorphism in terms of volumes.
Why do you take logarithm?
Actually, instead of log m, we can consider m. In that case, it is called volume growth, and it measures exponential growth of volume grossness. But sometimes it can be 0, because some diffeomorphisms are not growth like exponentially. So we want to measure some polynomial growth, so we just take here log m. So I mean,
numerator log is also the same reason. And the numerator log, you are taking log of measure volume, right?
Yeah, log of measure.
Is that the same thing, same reason?
Yeah. So if this function is linear function with respect to variable m, then this measures polynomial growth. Other questions? Okay, so this was definition. In fact, later it does not depend on the choice of metric, so we don't care of what the metric is. Okay, let's see some examples. The first one is quite stupid, but it is very important example because this is only one that I know how to compute it exactly. So obviously we know that the slow volume growth of identity map vanishes because it already stable. And we consider the second example. So I want to use whiteboard. So we consider some so-called twisting map, but if you know the Dehn twist, then it is Dehn twist. So what does it do is following. If you consider some fiber like this, so this is L of x, so base point is x, then if you apply the Dehn twist, then we just wrap around this circle at once. So if you have another fiber, then it also wraps around this circle. So this is what I call a twisting map, and we want to investigate the slow volume growth of this Dehn twist. So actually it is very difficult to compute slow volume entropy. So I want to find its lower bound. So in order to find the lower bound, it suffices to consider some cube and its volume behavior. So as you can see, if I consider volume of cube under the map tau, then you can easily believe that this is almost same as the sum of two volumes. One is the circle, volume of circle, because this wraps around, and you have volume as the previous fiber. So you can easily believe that this holds. And if you consider its iterations, then you can see that, for instance, if you consider power of Dehn twist, then it wraps twice. Right? So you can see that the behavior of this iterated volume is given like this. So in this equation, you can see that this is a linear function with respect to the iteration m. So you can easily conclude that the slow volume growth of this map has lower bound 1. Of course, one has to, if you want to compute this number exactly, then you have to investigate all embedded cube, but this is quite difficult. And, okay, this is first. And secondly, we can try to compute the second slow volume growth. This is first slow volume growth because we consider one-dimensional cube. But for any two-dimensional cube, and if we consider any of its iterations, then it is bounded by the volume of support of a given diffeomorphism. Because this cube is top-dimensional cube, so its volume should be bound by the support of given diffeomorphism. So actually, this means that the slow volume growth of the twisting map of dimension 2 vanishes. Yeah. Actually, this is always true for any diffeomorphisms. Okay. Okay, now we are interested in finding a lower bound for slow volume growth because it is too difficult to find the exact number. Okay. Actually, the previous idea is kind of topological argument, but sometimes we need more efficient method. So let's consider some alternative argument. We first observe that the intersection of some fiber, fixed fiber at X, and another fibers which is different from Y. If we consider its two intersections and numbers, then it equals to M. So what I mean is that this was a fixed fiber Lx, and if we consider another fiber, say Ly, then you can see that these two intersect transversely, and it has two intersections. And this happens for all Y except the fixed Lagrangian, the fiber. Oh, sorry. Okay, this is very simple observation, but this implies that the volume of M iterated fiber should be larger than M times of S1, the volume of S1, because we observed it wraps M copies by means of intersections, so we can conclude that this inequality holds, so we obtain the same result. And this alternative argument is very useful to apply the symplectic geometry. So we will use this kind of idea. So this is symplectic viewpoint. We view this intersection as an intersection of two Lagrangians inside cotangent bundle of circle. Actually, the manifold S1 times R, the infinite cylinder, can be seen as the cotangent bundle of a circle. So, and also it is known that these two are Lagrangians. And of course, this Dehn twist is symplectomorphism, so you just regard this as an intersection of two Lagrangians. And then, thanks to the first talk, we know that the generators of Lagrangian flow homology of these two Lagrangians are given as intersection points. So, of course, this will be explained later. And so the dimension of the Lagrangian homology gives the lower bound for the number of intersection points. So that this, if I can compute the length of Lagrangian homology, then we can know this information. So though we can apply this alternative argument. So this is one way to apply the symplectic topology. And so today I want to concern the slow volume growth of a fibered Dehn twist. So we have to define it. So before defining the fiber Dehn twist, we need the manifold. So the symplectic manifold with boundary is called Liouville domain. If there exists one form, actually this is called Liouville form, on the symplectic manifold, such that if I take exterior derivative, then it is symplectic form. And if I consider the vector field, which is omega dual to lambda, because omega is non-degenerate form, so we can consider its dual. So its dual vector field is X. And if this Liouville vector field points outward along the boundary, then this is called Liouville domain. You can roughly think Liouville domain as the symplectic manifold with nice boundary. actually, the nice boundary means that if I have a Liouville domain, then its boundary naturally has the contact structure, so it is contact manifold. I don't want to define what the contact manifold is, but this is kind of odd-dimensional cousin of symplectic manifolds. And for a contact manifold, we can define the Rabe vector field, which is very similar to the Hamiltonian vector field in symplectic geometry, and it is defined as the following equations. But I will give some examples which can understand these examples. Okay, so before I start to give some examples, let's see some property on the some definition on the Liouville domain. In order to define the symplectomorphism, which is called fibered Dehn twist, we need a special circle action on the boundary. So we impose the following condition. So we say that a Liouville domain satisfies the condition P. Actually, this word letter P comes from the periodic. So if the contact boundary has a periodic ray flow, so if I consider the Rabe vector field as defined before, then we can consider its flow. And if this flow is periodic, then we say that the Liouville domain satisfies condition P. So this means that for this Liouville domain, we obtain some circle action on the boundary. So this means that we have very interesting symmetry on the boundary. Okay, then I want to define the fibered Dehn twist. So let's consider a Liouville domain with condition P. Then the symplectomorphism will be called the fibered Dehn twist if it constructed as the following feature. So I want to explain what the fibered Dehn twist is. Actually, this is some natural. Sorry. Oh. Okay, this is correct. Okay, actually, this Riemann surface is Riemann surface with boundaries. Typical example for Liouville domain. So let's consider this example. And we know that near the boundary, it has Kola neighborhood. So we assume that it is kind of diffeomorphic to this interval times boundary. Then the Dehn twist is defined as follows. So inside the interior, Dehn twist is identity. And here we also impose that Dehn twist is identity, and near the boundary it is also identity. This is very important condition actually. And here we define Dehn twist, a fibered Dehn twist as follows. So if I consider t comma x, then on the first factor we just go like identity, but on the second factor, I mean the boundary factor, we just apply the S1 action. So here we consider the flow of Rabe vector field with time t. So this is kind of fibered Dehn twist. So I want to explain what Dehn twist do, what fibered Dehn twist do. So if you consider this kind of interval, and if I consider its image under the fibered Dehn twist, then this will be identity, because this map is identity. But if I pass through this region, then we do S1 actions. So it looks like this. Actually, in this picture, it is exactly same as the previous Dehn twist. But for high-dimensional examples, in general, there's no relation between the Dehn twist and fiber Dehn twist. So this is the definition of vague definition of fiber Dehn twist. Because we assumed that the action comes from ray flow, we can prove that this fiber Dehn twist is actually symplectomorphism. This is why we impose rape condition. So this is kind of special S1 action. Okay, so everyone likes example, including me. So let's see the first trivial example. But this is trivial but very important. So we just consider standard 2n-dimensional ball with standard symplectic form. Then this is symplectic manifold with boundary, and actually this is known as Liouville domain with condition P. And its boundary is, of course, diffeomorphic to the sphere, and the S1 action induced by the ray flow is, in this case, a Hopf action. So this forms a Hopf vibration. And let's consider the second example. This is the complement of hypersurface in the symplectic manifold. So here we consider closed, I mean there's no boundary. So we consider closed symplectic manifold with integral symplectic form. Usually symplectic form lies in the drum cohomology, so we have to consider R coefficient, but here we assume that it lies in integral coefficient. This is some kind of technical assumption, but it is not quite important. And we consider symplectic hypersurface Poincare dual to this class. You can see that this is some symplectic analog of smooth projective variety and the ample divisor, ample hypersurface. And then if you consider the complement of this symplectic hypersurface, then it naturally carries the Liouville domain structure, and each boundary has periodic rape action. And actually this boundary is S1 bundle over this symplectic submanifold, and of course rape action coincide with standard S1 action on this circle bundle. And the final example is quite interesting. We consider AK singularity, which means that we consider so-called AK polynomial and its variety. And if I consider some big ball inside this complex affine space, and we intersect with this AK singularity, then this becomes a Liouville domain, and its boundary has periodic rape action. And actually, the boundary is called the link of AK singularity. But I don't want to talk about this.
Does that AK has singularity? Does that AK has singularity? Is it equal to 1 as well?
No, this does not have singularity.
It's equal to 1?
Yeah, equal to 1. In order to avoid some singularity happens at the origin.
Singularity is the origin.
Yeah, origin.
So the AK has no singularity.
Yeah, in this case we take 1, so there's no singularity. Okay. So now our question is the following. Is there an uniform lower bound for the slow volume growth of symplectomorphism on this special kind of Liouville domain? So we want to investigate in this example we investigated the lower bound. So we wanted to investigate the lower bound in these examples. And we answer this question as following. So we answer this question on the component of fiber Dehn twist in the group of symplectomorphism. So I have to explain something. Okay, so if I consider Liouville domain with property P, and then we can consider group of symplectomorphisms. Actually, this means that it consists of all symplectomorphisms, which is identity near the boundary. Then it looks like this kind of picture. So this is group of symplectomorphisms, and here we can always find identity map, because identity map is clearly symplectomorphism, and we know that there is symplectomorphism which I defined before, the fiber Dehn twist. So we also have fiber Dehn twist and the power of fiber Dehn twist and so on. And so here we answer this question as following. We show that every connected component of fiber Dehn twist are different. So all connected components of fiber Dehn twist are different. And if I consider some symplectomorphism phi, which is symplectically isotopic to the fiber Dehn twist, then we will show that this also has some lower bound for slow volume entropy, slow volume growth. This is true for all components. So this is what I mean. The word component means. This is component in the group of symplectomorphisms. Okay, so I already mentioned this more precisely. Okay, this research are already done in many.
The volume growth is independent of symplectic isotopy, or?
No, it does not mean this, because we obtain same lower bound, but we don't know whether they are exactly the same. Yeah, lower bound only. Okay, so the Porterovich showed that obtains some lower bound for these kind of examples, and actually Frauenfelder and Schrenk proved that similar question for Dehn-Seidel twist. Actually, Dehn-Seidel twist is generalization of Dehn twist, and actually our work is inspired by their work. Okay, so I have no time, maybe 10 minutes. Okay. Okay, I want to briefly explain what the vector flow homology is. This is kind of flow homology for non-compact manifold. So here we choose Liouville domain and we choose some Lagrangian L, but it has to be admissible. So maybe I can use this picture. Okay, this is our Liouville domain, and we consider the following Lagrangian, which is admissible. Admissible means that it has nice intersection near the boundary, so that we can extend. At first, we attach infinite cone on the Liouville domain. I mean this piece. So we make it non-compact manifold, say W hat, and because Lagrangian is admissible, so we attach cylindrical cone, so we obtain infinite Lagrangian R hat, and then we choose some admissible Hamiltonian, so I have to explain what the admissible Hamiltonian. So on the completion, we define the Hamiltonian. So inside the interior, Hamiltonian is almost same as zero function, and on the infinite cone we have some slope, and behind away from the compact domain it becomes linear function. This is typical example of admissible Hamiltonian. So if I have this admissible Hamiltonian, then we can consider its time-on flow. So I will consider time-on flow. So let's consider the time-on flow of Lagrangian. Then because this Hamiltonian is very small inside the interior, so it is almost same as the previous Lagrangian. But as long as we go out the interior, then it has some wrapping. So it wraps like this. Mm-hmm. Okay, let's stop here. Okay, we have this wrapping. So this this red means that it is the image of Lagrangian under the time-on flow. And actually here we want to do Lagrangian flow homology for these two Lagrangians. This is what we call vector flow homology. So here we choose some almost complex structure, but this is not quite important. And we consider some path space from L to L. We just consider all open string from L to L, and we define some action functional. But importance is that the critical point of action functional corresponds to the set of Hamiltonian codes. And Hamiltonian codes means that it is open string, but it satisfies Hamiltonian equation. And the importance is that critical point of this action functional corresponds to the Hamiltonian codes, and Hamiltonian codes are corresponding to the intersection point of these two. So we want to investigate the intersection point. So the chain group is defined to be G2 vector space generated by the Hamiltonian codes. This means that we make chain group as the generators of these kind of intersections. So generators are all of these intersections, and the boundary map is defined naturally. Actually, this is kind of Morse theory. So we consider moduli space of flow strips from X to Y. So we can count this moduli space. So it has number, and we count its number mod 2, and we obtain some number, and we consider this Y. So anyway, we can define the boundary map. And it is known that for generic choice of Hamiltonian and almost complex structure, this boundary map is actually boundary map, which means that it is square of this map is vanished, so we can define homology. But you can see that in this picture, we can't see all intersections because we have chosen linear function, so it has no intersections behind the compact domain. But in fact, geometrically, we wanted to see infinite wrappings. So here we just take a direct limit on this flow homology group to obtain the genuine flow homology group. And it is known that it does not depend on the axillary choices, and it is invariant up to Hamiltonian isotopy. So it is very nice invariant property. And there are two types of generators. I mean that the first type is intersections inside this type, and the second one corresponds to the intersections on infinite cone. And the main property is that if Liouville domain satisfies the property P, which we explained earlier. In this case, the second type generators corresponds to the intersections of Lagrangian and the fiber Lagrangian under the fiber Dehn twist. So we obtain this relation. And if you remember the previous symplectic idea, then you may get some hints to apply this technique. And so the dimension of vector flow homology gives a lower bound for intersection points of this kind of intersections. Now I will explain what our main theorem is. So let W be a Liouville domain with the property P, and we assume this special condition, but this is not quite important because we found all examples which satisfy this condition. And then we suppose that we can find very nice Lagrangian such that L is diffeomorphic to this n cube, because we have to know the slow volume growth. So we impose this condition. This is a diffeomorphic to n cube, and we have this strange condition. But you can believe that this guarantees that it has sufficiently many lengths so that it guarantees it has many intersections. Because in this picture we saw that many intersections apply the lower bound. So this guarantees that the same thing. And then for any symplectomorphism which is symplectically isotopic to some power of fiber Dehn twist, then this map also have same lower bound. So we obtain this lower bound. And the main theorem B is that we found many examples which satisfy this condition. So main technique is Morse-Bot spectral sequence. So we constructed Morse-Bot spectral sequence for vector flow homology, and we computed it. So I'm sorry, but I have to explain. So many examples are coming from real symplectic manifold. Suppose that we have antisymplectic involution, which is involution, but it is antisymplectic. If symplectic manifold has antisymplectic involution, then it is called real symplectic manifold. And the zero locus of this antisymplectic manifold is a Lagrangian, and it is called real Lagrangian if it is not empty. And actually, in our examples, we can obtain antisymplectic involutions. For the first case, we know that real Lagrangian is just Dn, and in this case, unfortunately, we have this vanishing vector flow homology, so our result cannot be applied. And here we can impose that there is antisymplectic involution on the symplectic manifold. Then we can see that the complement also admits so nice Lagrangian. And same happens at the classical complex manifold. And I have to summarize this talk. Fortunately, we did not use a nucleic bomb to kill mosquito. What this means that someone may ask that, why do you use this big machinery to show this uniform lower bound? Because sometimes it can be done by using some topological idea. But the thing is that this is not the case, because we found there are examples satisfying the main theorem, but some power of fiber Dehn twist is smoothly isotopic to identity map. So what this means that smooth isotopy does not guarantee a uniform lower bound for slow volume growth, because if fiber Dehn twist is smoothly isotopic, assume that fiber Dehn twist is isotopic to identity, but we know that this has lower bound 1, at least to lower bound 1. But here identity map has lower bound 0. So there's no relation between two slow volume and growth. But if they are connected in a symplectically, then we can see that they share same lower bound. So this is what we call genuine symplectic phenomena. Okay.
The definition of this volume growth is used using symplectic structure.
No, it does not use symplectic structure. Just Riemannian manifold.
I see.
Yeah. But if we impose symplectic condition and if we observe special symplectomorphisms, then we observe this kind of interesting result. Okay, so I'm sorry for delaying, but thank you for your attention, and I again appreciate organizers.